All right, I've got another differential equation on the board corresponding to a forced harmonic oscillator. The forcing function here is cosine of 3t. We still call this sinusoidal forcing. It's not cosinusoidal forcing, it's just sinusoidal forcing. Okay, so I know my general solution is going to be a solution to the associated homogeneous equation plus a particular solution. Okay, so let's find the solution to our associated homogeneous. Is y double prime. Oops. I'm sorry. That was supposed to be a 4 there. Okay. There's a 4 there now. Y double prime plus 4y prime plus 6y equals 0. So my characteristic equation is s squared plus 4s plus 6 equals 0, which does not factor. So I shall use the quadratic formula. S is the opposite of 4, plus or minus the square root of 4 squared is 16, minus 4 times 1 times 6 is going to be 24, all over 2. So that's negative 4 plus or minus the square root of negative 8 over 2. That's negative 4 plus or minus. I'm going to pull out an I because this is negative. And then square root of 8 is just 2 root 2 all over 2. Now what's nice about that is I can factor out a 2 on the top, so I'm going to have 2 times negative 2 plus or minus I root 2 over 2, and that's going to cancel. So I get negative 2 plus or minus I root 2, and those are my solutions. Okay. So remember what we need to do then is we need to say, okay, that's going to give me enough information to get a complex solution, and then from that complex solution I can get 2 real solutions, because both the real part and the imaginary part will be real solutions to this. So a complex solution, and I'm going to just go with the notation that I put a tilde on my complex functions. The other option is to put a C as a subscript. I did that earlier and I decided I just didn't like it, but that's what the textbook does. Either one is totally fine, whatever you prefer. But this would just be e to the negative 2 plus I root 2. So I pick one of my solutions, and that allows me to form a complex solution. If you wanted to pick the other solution, totally fine. We're going to get the same or an equivalent version of the general solution to Might look different, but it will be equivalent. Okay, so notice, oh, and I'm sorry, times t, it's a function of t. Okay, so that's e to the negative 2t times e to the I times root t. And then I'm just going to use Euler's formula on that. So that's e to the negative 2t times cosine of root 2t plus I times sine of root 2t. So that's e to the negative 2t cosine of root 2t plus I times e to the negative 2t times sine of root 2t. So this is y tilde, the real part, and this, not including the I, is y tilde, the imaginary part. So those are both solutions, real valued solutions to A, okay? And my general solution is just an arbitrary linear combination of those. So we're going to get k1 copies of e to the negative 2t cosine root 2t, root 2 of t, plus k2 copies of e to the negative 2t sine of root 2t, plus, oh my goodness, what we're going to put there is our particular solution. Okay, so we want to find our particular solution to this differential equation. And what we can notice is that cosine of 3t is the real part of e to the I3t. So I'm going to complexify. I'm going to say y tilde double prime plus 4y tilde prime plus 6y tilde is equal to e to the 3it. Okay. And then if I can guess that my particular solution to this complex equation, I would guess that that's a copies of e to the 3it. I now know that the particular solution to the real value equation will just be the real part of yp tilde. Okay. Excellent. And basically that's just because differentiation, if you start with something real and you take the derivative, you get something real. If you start with something imaginary and you take the derivative, you get something imaginary. So the process of differentiation and the process of multiplying by 4 and by 6 doesn't mix up the real parts and the imaginary parts. So I can just work with the real part, I'm going to get something that works. I can work with the imaginary part, I'm going to get something that works. Okay, so if this is my guess, then yp tilde prime, good grief, is going to be 3ia e to the 3it. Yp tilde double prime, now I'm going to bring down another 3i, so that's going to make it a 9i squared, which is negative 9a e to the 3it. So now I'm going to plug that into my complexified equation. It's so much fun to say that, isn't it? So we're going to have yp tilde double prime plus 4yp tilde prime plus 6yp tilde is going to equal e to the 3it. So yp tilde double prime, that's negative 9a e to the 3it. Plus 4yp tilde prime is going to be 12i a e to the 3it. Plus 6yp tilde is just 6a e to the 3it. And that's going to equal 1 copy of e to the 3it. But here, if I factor out the e to the 3it, you can see how many copies of that I actually have. Here I've got negative 9a plus 12ai plus 6a copies of e to the 3it is equal to 1 copy of e to the 3it. That's going to be negative 3a plus 12ai copies of e to the 3it is equal to 1 copy of e to the 3it. And of course that's only going to work if the coefficient here matches the coefficient here. So negative 3a plus 12ai has to equal 1. That means that a times negative 3 plus 12i is equal to 1. That means that a is 1 over negative 3 plus 12i. So we've solved for our a here. We just have a complex number, and it's not in a particularly user-friendly form. So I want to get that into standard form. So if a was 1 over negative 3 plus 12i, I'm going to multiply by 1 in the form of the conjugate over itself. That's just the same two terms connected with the opposite sign. So it'll be negative 3 minus 12i over negative 3 minus 12i. It amounts to just changing the sign of the imaginary part. So that's going to give me negative 3 minus 12i over, oops, oh, that's just hanging out. I don't know why that's there. Okay, over negative 3 times negative 3 is 9. The outsides and the insides cancel. That's the beauty of this. This is going to give me negative 144i squared. That's negative 144 times negative 1, which is positive 144. So that's going to be negative 3 minus 12i all over 153. Oh my goodness. So I'm just going to distribute the division because I like to have my real part plus I times my imaginary part. So that's negative 3 over 153 minus 12 over 153i. And I can reduce because 3 goes into this. So this is negative 1 over 51 minus 4 over 51i. That is my lovely a written in its standard form of real part plus I times the imaginary part. So I now know that yp tilde is, plugging that in for a, negative 1 over 51 minus 4 over 51i times e to the 3it. All right, I need to work this out some more, so clearing some space. Okay, so that is negative 1 over 51 minus 4 over 51i times, using Euler's formula, that's just cosine of 3t plus I times sine of 3t. So if I FOIL that out, I'm going to get negative 1 over 51 cosine of 3t. I'm going to underline that because that's real. Okay, and I want, this time, the real part. Okay, minus 1 over 51 I times sine of 3t. I don't really care. That's imaginary. Minus 4 over 51 I times cosine 3t. I don't really care. That's imaginary. Minus 451 I squared is plus 451sts sine of 3t, and that is real. So these two terms that I've underlined are going to give me my real part. So my real part, which is my particular solution to the real valued equation, is going to be negative 1 over 51 cosine 3t plus 4 over 51 sine of 3t. So my general solution was a solution to the associated homogeneous plus my particular solution. Now I had written my y sub h right here. I had left myself this much room for writing my particular solution. So I think what we'll do is we'll just carry this over to the next line and say this is plus, well, actually I can say it's minus 1 over 51 cosine of 3t plus 4 over 51 sine of 3t, where this is the particular solution that we just found. Excellent. Okay.